can see that just from the graph. And then once we go to the chart here, and then when we go to graph the data, it makes even more sense, or it should. So we can see that this is actual linear data, and that the data doesn't change, the slope doesn't change. And we've also talked about how the slope of a position time graph gives you the velocity. So whatever the slope of position time will be is your actual velocity of that particular object. So that's notes from last time where I detoured and said, okay, the slope of a position time graph is your velocity. Let me see if I can pull that up real quick. Yeah, so I did a detour and stated this as a general rule for understanding what velocity is. So we can see that the slope of a position time graph, once you have your data graphed, and we're going to graph it again, position versus time, and anytime we take the slope of that position time graph, we are going to get the velocity. So let's say the slope is 5. We know physically that's going to be 5 meters per second for average velocity. And likewise, when we get to it, when we graph velocity versus time, the slope of that graph will give you the average acceleration. Average, basically, because we're looking at the final position, the final points minus the initial points. That's your average. But in real life, you're not always cruising along on the street. Sometimes you speed up, sometimes you slow down, sometimes you go at a constant speed. So in those instances, you have what is called instantaneous velocity, or even in some cases, instantaneous acceleration, but we won't deal with that explicitly in this class. So any questions on these definitions? So anytime we take the slope of PT graphs or XT graphs, we get your average velocity. And likewise, the slope of VT or velocity time graphs is the average acceleration. Okay, back to now the important guy. We can see this again, right?
Yes.
Okay. Graph your data. Yeah. So now we've taken the data from the chart, understanding that this data is linear. The differences between the positions are the same. 5 here, 5 there, 5 there, 5 there. And that tells us right away, okay, we should be getting a line of some sort. So this best fit line that we're now graphing, this guy is the one in question. Let me erase this one here, because that was just an illustration of another thing. So we plot the points as we did in our math classes, 1 to 5, 10 to 2, 15 to 3, 20 to 4, and then we drew a line of best fit. Physically, this line of best fit is your average velocity. So in this case, all of the data points fit nice and neat. In real experiments, or most experiments, they won't fit all on the line. But what we're still going to do for all those data points is to draw a line of best fit anyway, a line that goes through those data points, even if all of the data points fall outside of that line. So we have, let's say we have line dots here, dots there, wherever, we're still going to draw a line that best fits the points. That's why it's called a best fit line. For these linear data points. And then we translated the math equation, slope-intercept form of a line, equation of a line, into an actual physics equation. We knew that on the y-axis, which is the left column, represents our positions. our position, which is represented by the variable x. Slope here represents our velocity. Why is that? Because velocity is rise over run, change in x over change in time, where x is in the y-axis and time is in the x-axis. So that's why t is here, represented in the x-axis. We do not have a y-intercept for this line, so that's why this is 0. Or we can just not write it. So our equation of this line in physics terms will be x equals vt. Position is velocity times time. And we also know that just by rearranging the equation for velocity. Velocity is x over t. You solve for x, it's x equals vt. So same. So this was that second line with the y-intercept, which we saw last time and which we'll see again today. So the equation of the best fit line is x equals vt. Questions there? That makes sense? That's clear? Comments, questions? All right, so we did all that stuff. Okay, so we'll come back to the motion map. Okay, now page 6, practice 2, comparing position versus time graphs. So since we're doing it all today, I want you to turn this in also today. So you got 2 things to turn in. You have your notes you want to turn in and pages 6 and 7. So good question. So we have a question. So is x equals vt the physics equivalent of y equals mx plus b? Yes, exactly right. We are translating math into actual physics, physical quantities. So this equation of a best fit line is no longer an arbitrary y equals mx, which is arbitrary number for slope. The slope means something. The slope is velocity. X is represented by time because time is in the x-axis. And y is position, represented in the y-axis. X versus t. Just like in math, you have y versus x. Okay, so again, in the y-axis, we have position. X-axis, we have time. Position, time graph. Position versus time. So consider the position versus time graph below for cyclists A and B. We asked the question last time. Do the cyclists start at the same point? You can see that they do not start at the same point. One starts at 0, the other starts at something other than 0. How do you know? That's what we see, right? If not, which is ahead? So as we answered last time, no, cyclist B starts at a point other than 0, and B is ahead. Okay. Now, at t equals 7 seconds, which cyclist is ahead? How do you know? Well, we see that they intersect at 5. That's your eigenvalue or your solution of your simultaneous equation, blah, 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 same thing, right? So at 5 seconds, they meet up. And then 7 seconds, we can infer that 7 coming after 5 there, that cyclist A is ahead by looking at the position. So it's kind of just analyzing the graph, interpreting this data. Which cyclist is traveling faster at t equals 3 seconds? And how do you know? So based on this, real quick, somebody chime in. Which cyclist is traveling faster at 3 seconds?
Cyclist B.
Absolutely. Cyclist B is traveling faster at 3 seconds. And how do you know?
Because he started ahead.
He started ahead and he has a a steeper slope at 3 seconds. So cyclist B travels faster, right? Now, faster meaning implying the velocity. Faster implying the velocity, which implies the slope, okay? The slope of position time graph gives you the velocity. So at 3 seconds, cyclist B's slope is greater than cyclist A. Therefore, cyclist B is faster at 3 seconds than cyclist A. So I hope we can translate that. Travels faster at 3 seconds. You can just write that in to that effect. Are their velocities equal at any time? How do you know? Someone else can chime in. Are their velocities equal?
No.
Absolutely right. Because the slopes are not the same ever. They meet the same position at 5. Don't confuse that with slope. You got it. Not equal. So velocities are not equal.
Mr. Kelly,
Yes.
what page are you writing on?
Writing on page 6.
Oh,
That's page 5.
Well,
Oh.
my page 6 here, whatever. Yeah, the page that says comparing position versus time graphs, whatever that is.
is that the one we were supposed to do?
Yes, that's the one you were supposed to do.
No, because for ours the numbers are different, and I think it's supposed to be your page 7. I did that one instead, because for us it writes 6 for that one.
Okay. Well, you do question 3, comparing position time graphs. We're doing it all together now, so next time we can be on the same page.
All right.
All right. Yeah. So, and then E. Let's see. My formatting was all off, when I saved it from PDF. But we'll figure it out. What is happening at the intersection of lines A and B? Let's see, can I get a regular cursor? So what's happening in part E when they intersect, when the lines intersect? Any guesses?
They were at the same distance.
Yeah, they're at the same point. Yeah, that's exactly right. So they meet up for 1 second and then they pass each other. So then so A and B are at the same position, since using our lexicon: position, distance, displacement. So they meet up at the same point. Okay, so now number 4, consider the new position versus time graph below for cyclists A and B. So we're looking, so this was the previous, and now over here. How does the motion of the cyclist A in the new graph compare to that of A in the previous graph from page 1? I think we answered this last time. So we can say this time cyclist A starts from a position other than 0, because last time A started at 0, as we can see, and now it starts whatever that could be, 25, doesn't matter. So it starts at a position other than 0, or it starts at a position where x is not equal to 0. So we don't care what that number is. It's just, we know it's not 0. All right, then, how does the motion of cyclist B in the new graph compare to that of B in the previous graph? It's
Nothing changed.
It almost looks the same.
absolutely right. The slopes are the same. That means the velocities are the same. Same, all that. It pretty much seems like it could meet at the quote same position if we're gonna treat this to scale, but we don't have to. Good job, guys. Nothing changes. Same slope, same velocity. Okay, so I'm just that translation. First of all, I got to know what I'm looking at, x versus t. Okay. You know, like some kind of method, right? You can think about this if you're doing the problems later. What graph is it? Okay, I've identified x versus t. Something like you can ask yourself, what's the slope? Whatever the slope is, this thing wipes out. What's the slope? The slope of a position time graph is the velocity. In this case, slope equals velocity. Now, something like that, those 3 points you can put on your paper, you know, notes, you know, doesn't have to be part of the homework assignment, but just keep that in mind. The graph is it? What is the slope? In this case, xt, the slope is the velocity. If it's vt, the slope is the acceleration. That's down the road. Which cyclist has the greatest speed, and how do you know? Think about slope in the new graph.
Cyclist A still has the faster faster speed.
Absolutely, Sophia. Absolutely right. Even if it's a negative slope, its velocity is still greater because the slope is greater. You know, we have a steeper slope where the positive or negative, therefore A is still moving faster. In this case, it's going towards the west, though. It's starting in the easterly domain, but it's going backwards. Let's say it starts at 20 and it's going all the way down to the origin. So it's going all the way backwards, and it can cross the origin and go to the west, and, you know, all that good stuff. So cyclist A has the greater speed. Since it has the greater slope, even though it's negative. Describe what is happening at the intersection of lines A and B. So again, it's the same thing. When you say they meet up.
They
Like,
meet up at the same distance at the same time.
yep. Technically position because they're meeting up at one point, but yep. So
Mr. Kelly, for C through E, is it talking about the both graphs or just the new graph?
just a new one. Yeah.
Okay, thank you.
Yeah. Yeah. T equals 5. So which cyclists travel a greater distance during the first 5 seconds? How do you know? First 5 seconds. So that one's a tiny bit of a challenge, huh? Which cyclist traveled a greater distance during the first 5 seconds? So they meet up at the same point, but they don't necessarily travel the same distance. Oh, it looks like cyclist A travels this greater distance. Because relative to the meeting point, we can see that B, the slope is going to be not as steep as A. So even though they meet at the 5-second point, A is traveling a greater distance before they meet up. So does everybody see that? Any questions about that?
No, sir.
So yeah, so cyclists, cyclist A travels greater distance. Okay, so that's your 6 and 7. So you turn that in as well as additional notes that we'll take today. Right. So okay, let's go back up to get a chance to write that. Let's go back up to the motion map. The previous page. Boop, 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 boop. All right, so where it says number 1, practice 1, graphical representations of motion. So what we're going to do is we're going to analyze the graph at the left, and then we're going to draw in or write in a motion map on the right. So those points on the right graph represent positions. And so what we're going to do is we're going to draw a line that represents each position after every second. So given the following position versus time graph, draw a motion map with 1 dot for each second. So you start drawing a line. I'm going to start drawing a line, the upper part of this number line here. And eventually we're going to come backwards because position versus time, we increase our position here. We go from 0 to 4, and then we are still for like 1 second, and then we come back to the origin. So we want to represent that another way in terms of a motion map. So far we've taken data, we've observed something, we made a hypothesis. Oh, there's a relationship between position versus time. Okay, we collect our data into a data chart. Dependent variable on the left, independent variable on the right. And now we've gone to graph that data with position in the y-axis, which is the left column, time in the x-axis, which is the right column, graph the data, we represent that into a graph. So far we've done 3 steps with this data. We've collected it, we put it in a data chart, graphed it, and now we're going to represent it as a motion map. So all kinds of ways, and from the graph, we've created an equation. So all these different ways of understanding what's going on with this object moving at a constant speed. We know what the slope of a position time graph is the velocity. So we've dealt with that issue just a few moments ago. All right, so this motion map business. We look at this graph on the left, and we see how far it's traveled each second. So in the first second, it's traveled 2 meters. So here is 2 here. So 0, 1, 2, 3, 4, 5. And so I'm gonna start up here just in case because I don't want to start down here and it comes back and it's a little messy. But in 2 meters, we've gone 1 second. So we start from 0, something like this. You can write on paper, of course, and we represent we place a dot at the 2 meter mark because after 2 meters, it's gone. After 1 second, it's gone 2 meters. Okay, you guys following that? So we can even put an arrow like that because first of all, we're going from 0 to 2 and took us 1 second to do that. Next, in the second, we have traveled to 4 meters. So now we just keep on drawing and we stop at 4. Okay, so we go, come on. Okay, so like that. We're going to the right, we're increasing our position, 2 meters per second, at least so far. Now is a problem, or difference. At the 4 meter mark, what's happening between 2 and 3 seconds?
It stays at 4.
Exactly, it's at rest. You're at rest, I'm at rest. We're not moving. Time's moving. The 4th dimension is going. So we just represent that not as a right or left. We just say stay in place by drawing a line, vertical line, something like this. Okay, so for that 1 second, we're still at 4. All right. Then next, from 3 to 4, we go back to 3. So now it looks like we've gone from 2 meters every second, seemingly to like 1 every second now. Okay. It's decided to go a little slower. So now we go backwards, stop here. So hope you guys can see that. Hope you guys can track that pretty good. We're increasing our position, going to the right. The arrows are saying that we're increasing our position, then we stay still, and then we go back the other way. Staying still is, same thing as, it's in math where you cannot take the slope. It's non-differentiable in calculus. And you can't do anything with it. It's a constant. So we're representing those ideas with this vertical line. Can't take a slope. It's non-differentiable, which basically is the same thing. Undefined, all that. Okay, so 4 to 3, then we go 3 to 2, and another second. And okay, and then from 2 to 1. And then 1 to 0. We represented the entire trip. So 1, 2, 3, 4, 5, 6. At least those, those seconds. And the positions are below. So do we have any questions on that? Let's make sure we got it. Write it down. Consider it.
Can you give like a quick summary of it again? I kind of got lost in
Nope.
the middle.
No worries. Yep. Okay, in drawing this motion map, we have the positions. We're going from 0 to 5. Well, that's the extreme. We don't actually get to 5. And what we need to do is draw arrows that represent how far we're going every second. And once we get to that position, after 1 second, we put a dot. And so after the first second here, we've traveled 2 meters. So I go from 0 to 2 in 1 second.
Okay, I get it now. Thank you.
All right, so on and on. So let's just peruse this even further. Why don't you take the slopes, just do it independently. Give you a couple of minutes, whatever. Give me the slopes of these two lines, and then give me the velocities of those two lines. Should be pretty simple. Yeah, you can write it down on paper, and then once you've got it done, you can just tell me.
Wait, Mr. Kelly, we find velocity on what else?
Yeah, I just want you to give me, find the slope of both of these lines, and then tell me what the velocities are.
Okay, thank you.
Mhm. It's really the same thing. Slope is the velocity. Okay, so from 0 to 2 seconds, what is the velocity? Let's see, let's go with
2 meters per second.
absolutely right. 2 meters per second. Does anybody not see that? Okay, so we have velocity, delta x over delta t, which is the slope. M equals change in y, change in x, rise over run. So we're translating the math, which math is beautiful, math is great. It is. But what physicists do is we take the math that's necessary and we translate that to physics, physical quantities, so that we can better understand and communicate that to the general audience. Okay, so that we have a full understanding of what we're talking about. The more representations of the same data, the better. That just you know become a boss. Okay, so now we have 4 minus 0 over 2 minus 0. And that's positive 2 meters per second. Okay, positive 2 meters per second. What direction is it going?
Up.
East or west?
Well, forward and up at the same time.
No. One direction. East or west?
East.
It is going east because we know that positive numbers represent the easterly direction. Negative is westerly. So even though the other way back from 4 to 0, it's still in the so-called eastern domain, it's going towards the west. And another way that you know that it's going towards the west is this slope here will be negative. So what's the slope of the second line? You guys still see that? I just had a flash on my screen.
-1 meters per second.
Perfect. -1 meter per second. It is the slope is -1. In math, it'd be -1, turn your paper in. Physics, -1 meter per second because we're making it real. V equals 0 minus 4. And then we say 7, 7 minus, what do we got? 7 minus 3. Yep, so -1 meter per second. So that means the slope is -1, velocity is -1 meter per second. And what direction is it going? East or west?
West.
going to the west, going backwards, changing direction, all that works. Okay, so that's the number line there. And then we can say something to this effect, describe the motion. Again, another way of interpreting. This is why I like these worksheets, because there's multiple ways of interpreting the same data so that you can hopefully have a better facility in how to work it. You can probably do a slope of your line, and then I don't necessarily ask you to do a motion map, but you're gonna do it anyway because you're excited and motivated to do that. Motion map, and take the slope. You know that slope represents the velocity and directions, plus east, negative west. Describe the motion. All of that shows that you have a full understanding. Describe the motion of the object in words. Car moves at constant velocity from 0 to 2 seconds. It's still from 2 to 3 seconds. And from 3 to 7 seconds, it goes to the origin, goes back. Something like that. Doesn't have to be exactly that. Okay, so now in the breakout room in a second, we're going to go backwards. We're going to go from motion map to graph. We'll be doing that. So keep that in mind. Question 2, we're doing that in the breakout room. Okay, and then next thing we want to do. Oh yeah, boy, this one. Ooh. Okay, so I'm going to erase that beforehand. So in number 5, we're considering the following position versus time graphs. You know already this one here, the guy is at rest, speed, you have a velocity, etc. So what we need to do is to rank these situations from greatest to least displacement. Greatest displacement during the time from 0 to 10 seconds. Use a greater than, equal signs, but do not use the less than sign. So we're gonna have to get displacement. Remember, definition of displacement is final position minus initial position. That's all you're concerned with. Like that, right? Which is easier because in physics, that's all we're concerned with. Otherwise, for distance, we'd be, okay, we have to add everything. That's why distance is so cumbersome. Okay, I don't think I just did a couple of examples. So for example, for letter A, my displacement is just 0. 25, X final is 25 meters, initial is 25. 25 minus 25, 0, no displacement. Even though 0 distance as well. Yeah, and so I want you to do question 2 in your breakouts, and then also this guy, question number 5. Now remember, for distance, you have to add all the numbers. So it's like I wrote the definition here. I think distance, you're adding everything. So any questions before we break out? So hopefully that's better. You have, everybody should get full credit on the 6 and 7. Hopefully get full credit on notes. So start off on a good foot. All right, if there's no questions, let's assign the breakouts. There's like 30. All right. The 10 rooms of 3.
Wait, for the notes, we have to take a picture of what we wrote right now and send it to you.
Yeah. So most of the notes today will be on the paper, but just send it. Yeah.
Okay.
Mhm. All right, here we go. Breakout.
For the notes, are we sending it with the homework tonight or like from whenever you send the homework, like page 6 and 7? Are we also turning in the notes with it?
Yeah.
Alright.
Turn in notes with it. And yeah, and I'll remind you again, but I'd like to have that done so the class is over 11:50. If you've been taking notes, you should be able to turn all that stuff in by 12 o'clock. Right? So you don't need a half an hour. So okay. Open the room. All right, see you guys in 10. Okay, David, everything, let's go. Jorge, Sophia, let's go to rooms. Are you guys in? Okay. I see something different. Okay, let's start with number 2. All right. It's okay. We're doing this now for the first time, and once we get to our textbook, we'll go. The same concepts will be there, and a couple other things, but we'll be negotiating the textbook starting the week after next. We're going to go online. I want to make sure that everybody can access every bit of the software, the learning management system. So we'll probably spend like a full day just like making sure that, okay, I can log in. I can see your assignment, Mr. Kelly. I can see the notes. I can see the book. You know, there's all kinds of things. It's like, it's not the most user-friendly navigation, but that's why I want to spend time in making sure we can do it. Oh yeah, and that reminds me also, so keep this in your notes. We will be having our first exam next week. Okay, I thought the progress reports were the week after, but apparently they're counting the welcome week as week 1, where we did nothing. This is the surveys. I'll be telling you more about that on Monday. We had a question.
Are we gonna get the grades for our quiz from last time?
Yeah, I'll be finishing those up today, as well as some other things that I need to grade for you.
All right, thank you.
So we had a, okay, question. Okay, so now we went forwards. We went from the graph to motion map. Now we're going from motion map to graph. Given the following motion map, where position were recorded with 1 dot each second, draw the corresponding position versus time graph. So what we're going to do is, the way to look at this, look at the number line below. It says 0, 1, 2, 3, 4, 5. That's all your positions in meters. So it starts at 5 and it's going to go backwards. See, the arrow is going to the left. As I indicated here, down right there, with the arrow going to the left or west, right being east. But left is going backwards. Okay, so 5, we start at 5. And then after 1 second, got a little bunched up there, but you can kind of tell that 11 is this line here, right there. 12 is the last guy. So 5 to 4 in 1 second. So we start here and draw down like that. So after 1 second, after 1 second, so time lapse there. we're there. We went from 5 meters to 4. So that's what we're doing. We're translating the motion map of the motion of the object into the graphical equivalent. So far, so good. So 4 to 3 meters in 1 second, because the dot represents 1 second. 4 to 3. So at second number 2, we're at 3 meters. And then 3 to 2. 3 to 2. Okay, in the third second. So second number 3, 3 to 2. All right. So again, just to repeat, 5 to 4 here, 4 to 3, 3 to 2. And now we rest at the 2 meter point for 2 seconds because the 2 gaps, 1 gap there and another. So we're going to go from 3 to 5 seconds, 2 seconds at 2 meters. Okay, so we are at rest for 2 seconds. And then now we keep on going forward, dip down to 1 meter in 1 second. So is this making sense? Sort of. Excellent. Let me know. But is this, I think that was what, Anthony, right? Are you seeing that, or anyone else to chime in? Make sure you're understanding it.
Mr. Kelly.
Yes.
So when it's at a constant rate and there's 3 dots instead of just 2, does that mean it's 2 seconds, not 1?
Absolutely, right. So right here, it's at rest at the 2 meter point. If I can write. Yeah, you get that idea. Yeah, so 3 dots, yes, you can see that, but it's the gaps, there's 2 gaps representing 2 seconds. So it's a 2 meter mark for 1 second here and then another second. And that's why I went from 3 to 4 and 4 to 5, because I'm at rest for 2 seconds. Okay. So now I go from 2 to 1 meter in one more second. And I go from 1 to 0. So I'm now at the 7th second, and you can track it if you wish. 1, 2, 3, and this would be 5, 6, and 7. Okay, so everything's checking out, right? So 1 to 0. We're now at the origin after 7 seconds. Now we're at rest at the origin for 2 more seconds, just like before. We do that. Hopefully everybody's following. At the 9th second now. Now from 9 to 10, we increase our speed a little bit. We're not going 1 meter per second, but it's like around 2 meters every second. So in second number 10, from 9 to 10, we go from 0 to 2 meters. So 2 meters being there. Get up like that. And then we go from 2 to 4 for 2 more seconds, from 9 to 11. Something like that. So that's what our graph should look like. This is the graphical equivalent of this motion. Little lapse there. Any questions? Shoot, comments? See it now. Okay, what I'd like you to do on your CVPM, constant velocity particle model, I want you to calculate the slopes everywhere and write them down as velocities. Take a minute to do that. What kind? Oh, go ahead. Go ahead. Yeah, I thought there was a question.
I was gonna say, so do like number 3, 4, 5, or just do the slopes of each one?
Do the slopes. Slopes of each line.
Okay.
Mhm. So what kind of slope is going from 5 to 2 meters? Positive or negative?
Negative?
Absolutely. Yep. Negative slope. But just go ahead and take that and we'll do it together. So those of you who are quiet or anything, you want to ask a question or don't know what you don't know, send me a private message. I have extra time after school every Tuesday. Now, I'm reserving that mostly for AP. Actually, no. Just if you have any questions, Tuesdays I'm here Tuesdays after school from 2:20 to 3:15. And you know, that can reach by email, private chat, Google Classroom. Just don't hesitate. There's all kinds of ways you can get in contact with me. Okay, let's do that real quick. So the slope of the first guy, it's going to be a negative slope. We can tell just by the line, and back to your algebra classes maybe. So we say that's going to be side. So 2, come on, 2 minus 5, and that time interval is 3 seconds, huh? 3 minus 0, 3, so negative 1. Math, turn it in, that's my slope. M equals -1. Physics, velocity is -1 meter per second. Everybody cool with the fact that there's no slope between 3 and 5 seconds? Zero slope here, nothing. What does that mean? Lala, what does that mean? If zero slope, what's happening to you for real?
That you were staying in the same spot.
That's right. Yep, you're staying still. You are at rest.
Wait, Mr. Kelly,
Yeah.
would it be like the same from 3 to 4 instead of 3 to 5, as in like time?
Yeah, it'd be same slope for both seconds. Yeah.
Okay, thank you.
Mm-hmm. We also have another negative slope from 2 meters to 0. So 0 minus 2 divided by 2. So another -1. So the first velocity, the first slope, V1 is -1, V2 is 0. I'm at rest. Okay. V3 is 0 minus 2 over 2 seconds minus 1 meter per second. What direction am I going in? -1 meter per second means 1 meter per second to the
West.
to the what?
To the west?
Yes.
Is that the right direction?
Yeah, exactly. We're going to the west because right now we're still on the x-axis. We're still horizontal. We haven't started dropping objects yet. So we're still east-west, east-west. East is positive, west is negative. So V4 is just 0. There's no slope from 7 to 9. Then from 9 to 11, I'm changing my direction. I'm going east. 9, 11. 9 to 11. E5. 4 minus 0 over 2. 2 seconds plus 2 meters per second. So that's what I'm doing. Those are my slopes. That's my graph associated with the motion map. You can do a description. So again, there's multiple ways to help you understand all this stuff very powerfully. Okay, so I hope so. So if not, ask away, chime in. I don't care how many questions you rapid fire. Just, I want to stay on something as long as we need to so that you can get it for future applications. Just for a physics grade. So minus negative slope there, 0, and a positive 1. So we were traveling to the west. Okay, for example, you leave from Glendale Valley and going towards Calabasas or something, going west. Rest at a gas station, get some snacks. You go even more west to Thousand Oaks, right? And you rest there 7 to 9 seconds, 7th hour to the 9th hour, and then you come back the other way. You come back home or almost home, and not quite Glendale, maybe Burbank at second number 11. So things you can play around with. Describe your motion. Okay, let's see how far we can get in the next part. Well, actually, we'll probably come back to this later because running down. But what I'd like you to do, okay, today we're gonna turn in the notes and page 6 and 7. You guys got that? By noon, just picture, upload. Homework over the weekend will be to complete this packet. Okay, I'll put the assignment up. We're gonna skip this because that takes a while. I wanna give you the examples of the next part. So you're scrolling down, packet, we're now at practice 3, multiple qualitative representations. So I'm reading all that. What we're gonna do at this point, for each box here, we're going to look at the XT graph, position versus time, and we're going to translate that to velocity, and then we're going to describe what's going on, and then write a motion map. So who other than Sophia Lala can tell me what's happening for the X versus T? Anthony, except Anthony, Lala, and Sophia. So anybody else? What's going on there?
Does it say constant at the same rate?
Well, something's constant, not the speed I think you're implying, but something's constant.
Okay. What about distance?
Not distance. It starts with a P. Position, right? Its position is constant. You're at rest. See that?
Yeah.
Position is constant. Let's say that this was -2. That means that whatever your origin was, you're sitting in your room, and let's say you have an origin is your bed, and you're 2 meters west of it. That's your position. You're staying there. 1 second, 2 seconds, 3 seconds. So you're staying constant. Position. What kind of velocity do you have, Tigran?
I'm not sure.
Okay, if you're not moving, how much speed do you have?
0, nothing.
Perfect. No speed, so you can write fat 0 or say 0 velocity. Because remember, the slope of position time graphs by definition is your velocity. There is no slope here. There's no rise, just run. So 0 over whatever is just 0. 0 slope, 0 velocity. You got that?
Yes, thank you.
Yeah, no worries, no worries. So I am at rest here. Motion map. Well, there's no motion every second. So one very inventive person in my AP class, yeah, you can just write an undefined line, you know, just, you're not changing the positions because these are all positions. Remember, these are all, so we just can write an arrow like this. I mean, I know it's a little weird, but that's pretty much the only way we can represent something at rest, by an arrow going straight up, an undefined line, no slope. Now for this one, it's a little bit trickier. I will just write this in. The next time, or very shortly after the next time, I'll give you some additional worksheets to help you translate from position time to velocity time to acceleration time. But for now, I'll just give this to you, or just ask the general audience, what position line or graph in position versus time, what graph is associated with this negative velocity? What do you think? Think slow. What kind of graph and position would I have to draw? Any takers? I will give this to you for now, and then we'll have practice in the near future for sure. It would be a negative, well, it would be a line like this, because we have to draw a line that has a negative slope in order to have this negative velocity. Does that make sense? Or chime in, or not sure about that one? Any feedback will do. But I will just leave that for the moment. Let's see if we can get an easier one, if that is a little tough to handle at the moment. But now we don't say the object is going towards the west. And the motion map would be something like this, because we're going to go from a high position to the origin there. So once you write that in, and then we'll conclude for the day on that. So this is our homework for Monday. Don't go anywhere. Complete packet to this page right here, okay? So you have other stuff up ahead to see. This is page 9, or this exercise. So yeah, so turn in your 6 and 7 today, your notes of today. And 1 second.